Hello, I'm Vince Gucic. I developed this canopy simulation model for pecans. I'll describe how the model works and what goes into it, what comes out of it. The purpose of the model is overall to help develop a decision support system for managing water and nitrogen and possibly pruning and so on for pecans. So it's very much process-based, using physiology, physics, and the structure of the canopy. That way it can be adapted to any given location as opposed to a statistical model. The model resolves a great number of processes, but they're all, I would say, robustly parameterized. A lot of these things are intrinsically known, like the spacing of the trees, the crown diameters, and so on. Other things, such as the stomatal control parameters, can be measured in the field, or one can make very, as I say, robust guesses for the values based on the experience in other locations, other studies. The whole structure of the model is the first 700 or so lines in the source code, which I'm highlighting here, are all the descriptions of the processes and the way that the model runs, a little bit about why it was done, and then the features. When we get down past all of the details about how the processes are represented, there is a flowchart of which routine calls which routine. Okay, so if you ever get lost, you can go back to this section. Okay. In order to run it, obviously you have to compile the source code. If you don't have the source code or the application that I've provided, it can run in Windows or other OSs. It will require that you have weather data for the simulation, the data on the structure of the canopy, and various physiological and physical data, leaves, soils, and so on. The program will create a slew of results files. Let me just show you. There's a directory here that shows the input data files, the source code, etc., plus a number of the output files. Let me show you some of these. The main one is what's called results, and it has these extensions that are just for historical reasons. For each Julian day and each hour, let's say this one, Julian day 182, which is July 2nd. This is also for the year 2010, the Tornillo Orchard. It will present the liters per hour of the central tree that's being simulated, the photosynthetic rate in kilograms per hour, the soil water content, which you can see eventually being slowly depleted. I set the soil depth artificially large here so that it never gets depleted, simulating good watering without worrying about putting in irrigation. Gives the water potential of the soil, the root, and then these control coefficients, which is how much relative change you get in transpiration E or photosynthesis assimilation A for a given change in stomatal conductance imposed with everything else held the same. It also gives you the soil to root transport resistance, which is important for stress responses. It gives you the factor by which stress has reduced overall stomatal conductance. Keep it pretty low here, pretty close to 1, that is. And then for iterating the canopy conditions, it tells you, going over here, the water vapor partial pressure in pascals that is in the outside air, and then the value that is inside the canopy after the self-humidification from transpiration that's been iterated to convergence does the same thing for air temperature. So it says, for instance, it was 30.7 degrees, but inside the canopy becomes 30.5 because there's some advection into the canopy. For intermediate process information, it will also tell you the average light level on all different leaf area in the canopy, and it will report the final convergence errors that it found in the canopy water vapor, partial pressure, and temperature, and the number of iterations it took to get to convergence. I'll explain the convergence a little bit later. So the way that you assemble everything for running the model is obviously you need the weather file. I took this particular weather file from a weather station near the Tornillo orchard, and let's see, here it is. This is one of the few fixed format files in the whole place. I could change that, but this is the way it runs. It's matching a format that used to be used on the NMSU weather site. So it gives me the month and the date. I took out the year because it's irrelevant. It just needs this month and day in order to get the solar angles. That plus the actual time of day and hour by hour. Then it gives you the temperature in degrees Fahrenheit, those barbaric units, the relative humidity as a percent, and the wind speed in miles per hour, which later gets converted to metric units. And then this is the solar insolation in Langley's per hour. There's some other stuff that's been added later in the file just for doing some tests. You can ignore that. Okay. Then you need a massive input data file.